It's truly an honor to be here on the occasion of Stephen's 75th birthday. And I know he just has these to look at us and see how much we've aged every 5 or 10 years. But it's also a wonderful time to talk about physics and about the great contributions that, as you'll see, really underlie a lot of what we still do every day that Stephen made to the subject. So I want to talk about how quantum information is affecting in a more and more profound way do we have a laser pointer, by the way, or a stick? Stick. That's wonderful. Yeah, so how quantum information is affecting how we think about the problem of quantum gravity in a more and more sophisticated and deep way, I think. And what I want to focus on today is, for the most part, how, as a byproduct of trying to understand how quantum gravity might work, we're actually discovering new results just in quantum field theory. And that seems a bit counterintuitive. Once it's just a quantum field theory statement, you can actually go out and try to prove it, and that has succeeded. So the proofs are really hard. And I'll try to describe that for you. But I want to start with a touchstone, of course, the area theorem for event horizons. And the reason is not only that it's Stephen's birthday, and it's one of his many great contributions, the fact that the total area of all event horizons cannot decrease, something he proved. It's because I want to use it as a sort of simple template that everybody's familiar with, that we can look at from a different perspective and sort of use as an example of how today's results have come about, where we've learned about quantum field theory from gravity. So just to review this, Stephen proved this theorem in 1971, and like all theorems, it uses some assumptions. And here a key assumption is the null curvature condition, or if you use Einstein's equations, the null energy condition, that the stress tensor twice contracted with a null vector that generates the horizon is non-negative. And this is, of course, true for you and me and everyday objects that we see. Now, this area theorem was underlying a very important development that happened soon after. Bekenstein was thinking about what happens when entropy falls into a black hole. You just dump your entropy into a black hole. You never hear about it again. So isn't that bad? Because we can effectively violate the second law of thermodynamics, or at least transcend it. And so he made this proposal, and of course very much inspired by Hawking's area theorem. What else can only ever go up and not decrease? He made this proposal that black holes themselves should be ascribed an entropy. He didn't know the order 1 factor here, but he did know that it had to be in Planck units, because those were the only units available. And he knew that he was making a statement about quantum gravity. He was saying something about how many degrees of freedom a black hole has. And so the idea was then that to an outside observer, when you dump your box of radiation into the black hole and get rid of some entropy, that the outside entropy would indeed decrease, but the area of the black hole would hopefully increase by enough to make up for that lost exterior entropy. And so Bekenstein's conjecture was that the sum of the two, which he called the generalized entropy, black hole plus ordinary entropy, would never decrease. And I just want to stress that really those developments, going back to Stephen and Bekenstein in more than 40 years ago, 45 years ago, already had in them the key equation that my talk today is still about, that good stuff happens when you add geometry to information. I mean, this is almost literally what is happening here. And we have a very broad audience, but for the experts, I should emphasize that to the extent that we understand this, and we understand it pretty well for a large class of quantum field theories, this sum is better defined than each term separately. So the von Neumann entropy of a quantum field restricted to the outside of some surface is divergent. The leading divergence is actually proportional to the area divided by the cutoff. And so you can think of this as a counter term that cancels this. Right? This term depends on Newton's constant, which also has an RG flow. And from what we can see, the the area is just the first of several counter terms, geometric local counter terms, that make the generalized entropy finite and not sensitive to the cutoff. So just to summarize what Bekenstein said, in the presence of black holes, we have to replace the ordinary second law with a generalized second law of thermodynamics, which really should have been called the second law still, because after all, he was just saying that black holes are another thing in the sum of things that we have to include when we worry about the entropy. All right. So now let's move on to Hawking radiation. I'm still in my story of what happened long ago. So of course, if you had believed Bekenstein, it would have been clear that black holes have to radiate by the first law. But nobody believed Bekenstein, including, at least Steve and I'm pretty sure did not believe him. And so he did his own calculation, where he just directly discovered that black holes radiate, and it was a very powerful calculation that also fixed the order 1 factor and determined exactly what the entropy of a black hole is by working backwards via the first law. Now, what I want to focus on here is the particular consequence of Hawking radiation, that the area decreases as black holes evaporate, which is sort of obvious. And at the same time, of course, violates Hawking's area theorem, which has told us that this wasn't going to happen. And this is possible because it violates the assumption that the null energy condition is satisfied. Turns out that the null energy condition is not satisfied in the vicinity of a black hole horizon. And there are many other examples in quantum field theory. I want to stress this is not so abstruse. I mean, you can write down quantum states that violate the null energy condition, in the standard model. I mean, it's not something that's so hard to do. Nevertheless, though, while the area theorem breaks down, Bekenstein's generalized second law still holds, because as the area is decreasing, entropy is being produced outside in the Hawking radiation. And as Page quickly showed, that's more than enough to make up for the lost area. So once again, the generalized second law holds, which is remarkable because, of course, Bekenstein didn't know about this process when he conjectured it. So now I want to just quickly summarize the lesson here. What this insight that the second law still holds in Hawking evaporation means is that we can actually look at the generalized second law from 2 different angles. We can look at it through Bekenstein's angle as fixing up a problem with the second law of thermodynamics. But we could also look at it through the angle of saying, well, there was an area theorem, it's broken, can I fix it up so that it works even with quantum corrections included? Right? In a sense, it unifies those 2 statements. It becomes the ordinary second law in the case where there's no black holes around, and it becomes the area theorem in the classical limit. But really, neither law survives on its own. You need the generalized second law if black holes are present and treated at the quantum level. OK, so far I've told you what I think are accurate facts. But maybe you've heard about the situation in the United States, and I'm supported by the US government. So I'm required to include some alternative facts. And so I'm now going to report on something that you've never heard before. It actually makes more sense than most of what Kellyanne Conway says. But it's still wrong. It's historically wrong, but it could have been in a very different civilization. In that civilization, the second law of thermodynamics had not yet been discovered when Hawking found his area theorem. These were people who took general relativity seriously and discovered that first. And so then, in that world, alternative Hawking discovers his classical gravity theorem involving the area. And they also discover quantum mechanics before they discover the second law. I don't know how plausible this is, but I get to say stuff like this. And having done that, he discovers that the black hole radiates, because he studies quantum field theory on this background, and his beautiful GR theorem is broken. And so he says, what can I do? Maybe that theorem was just sort of the leading term of a more general theorem that still survives when I include quantum corrections. And after a moment of meditation, he realizes that what he needs to do is add to the area another term which has to have dimension of the area, so it's going to multiply the Planck length squared, and then the exterior von Neumann entropy of the quantum state. And he realizes that that works. Okay, so now he has a wonderful theorem that works even for evaporating black holes, but then he says, okay, what if there's no black hole around? Then this term isn't there, but that term still is there. And so from gravity, after including corrections for quantum effects, I've learned something about quantum mechanics. I've learned the second law of thermodynamics. Now, there are a number of problems with this analogy, but that's roughly what we're actually going to do, starting from a different GR theorem in the rest of this talk. Okay, and it's again, I think in an alternate history, it could have happened this way, even for the area theorem. We could have discovered the second law of thermodynamics from the area theorem by going up to a quantum correction, then throwing away gravity and just getting a quantum statement. All right, so the statement here is that if we start with the classical focusing theorem, which is in a way much simpler than, and has been known much longer than Hawking's area theorem, we get a conjecture called the quantum focusing conjecture. And once we eliminate gravity from that conjecture, we get a highly non-trivial statement about quantum field theory that had not been known, unlike the second law of thermodynamics. And yet it's quite simple, actually. Okay. So in order to do this, I first have to stress, and this is something I've personally learned best from talking to Aaron Wall, but maybe it was clear more broadly, is that generalized entropy is really not something that we can only consider for the slices of black hole horizons or event horizons of some sort. Generalized entropy is something that's much more generally at least definable. You can just take any Cauchy surface, consider it a two surface that divides it into two sides, and consider the quantum state reduced to one side at its von Neumann entropy to the area of the surface you defined, and call that the generalized entropy of that surface. And whenever I make statements here, they're going to be valid with respect to either choice of side. At least I'm not aware of counterexamples that would depend on such a choice. But once we choose a size, we're going to stick to it, right? For example, now what we're going to do is we're going to take this surface and we're going to move it along orthogonal light rays up to a different surface, A prime. And then we can, of course, ask the question, how did the generalized entropy change, which is analogous to the classical question, how much did the area change, but now with this quantum correction added to it coming from the exterior entropy. And in fact, what we can do is we can do an infinitesimal version of that in two senses. First of all, make the deformation only very small and then divide by its length to get to sort of differentiate. And then also, the area that's not really shown here very well, but the area is, of course, a two-dimensional thing. You don't really need to deform along all generators of this null surface. You can just deform along one of them and make that cross-sectional area quite small and study what happens under such deformations. You'll have pictures, hopefully, showing this in a moment. So the classical GR theorem that I want to start with is the focusing theorem, so I should quickly remind you what the expansion is. The expansion of a congruence of light rays, so these are really a bunch of light rays coming out of, think of this as a sphere, but it doesn't matter. Okay, here's a piece of that sphere, just to show you one more spatial dimension. And here are the light rays coming out of it, so the light rays are going perhaps to the inside of the sphere, and so the cross-sectional area between neighboring light rays is decreasing. Okay, so the logarithmic derivative of the cross-sectional area is called the expansion, theta. And I'm going to actually start from not even what's usually called the focusing theorem in GR, but from a simplified version of it, which is even more primitive. It's just a statement that the derivative of the expansion is not positive if the null energy condition holds. Okay, and in physics language, that's the statement that matter focuses light. So you can't have, for example, parallel light rays suddenly starting to diverge. What you can do is they can start to focus if they encounter a matter object. That means they go from 0 to negative expansion, but you can't do the opposite. Okay. So once again, this is a classical GR theorem. It depends on the null energy condition, and of course, quantum effects can violate this. And the usual boring example applies: evaporating black hole. It's a counterexample to so many GR theorems. And in this case, again, what can happen is that you have light rays which are outside the horizon, but very, very close to it, so they follow it for a while the black hole is evaporating. The area is getting smaller, but then eventually, because they're slightly outside, they do make it out, and they start expanding, and so that's an example of a violation. So we could again ask, well, can I rescue my classical theorem? Can I correct it to account for such quantum effects? Okay. And we're going to turn the same crank here. We're going to replace the area with a generalized entropy. Well, you have to be a little bit careful about where you do that and where you don't, but roughly speaking, that's what you do. So the first thing we're going to need to do if we have a classical statement expansion is not negative, we need to define a quantum expansion and then say that that's not, that its derivative is not negative. Okay, so this quantum expansion is going to be a capital theta, is the rate per unit area at which the generalized entropy changes. So it's just the obvious generalization. Instead of asking at what rate does the area change as I move away from my surface, at what rate does the generalized entropy change. Though there's an important distinction in that the classical expansion is really defined completely locally near any given null geodesic. You can ask what are the other geodesics nearby doing. It doesn't matter what the surface looks like elsewhere. Here it does because the von Neumann entropy can change in different ways depending on how I've chosen my surface away from the point where I'm doing the deformation. For example, I might start including an electron or excluding an electron in the exterior of the surface that I'm considering, and that electron could be entangled with and purified by some other electron that's either on the inside or on the outside, depending on what the surface does elsewhere. It clearly can depend on things that happen far away. But so it's really technically a functional derivative. But it's well defined. So this quantum expansion, so here's another picture. Here are the light rays. I don't know if you can see them, it's a little fuzzy, but there's these black lines. Think of that as like a null plane, like t equals z or something in Minkowski space. Here is a two-dimensional cut. Here is one side. You're kind of looking at this from below, like so. Here is the outside. And now you're asking, well, if I move my cut a little bit up this way, how does the exterior entropy in the area change? Okay, so that's the quantum expansion. And so what you get is, of course, the classical expansion plus this quantum correction. Curly A is the size of this cross-sectional area along which we're deforming, which in the end always gets taken to 0. And this is the derivative of the exterior entropy with respect to the deformation parameter. Okay, so that's a quantum expansion. Now we're ready to make a conjecture. Okay, now we can do the simplest thing, which is to take the classical simplified focusing theorem, which depends on the null energy condition, and conjecture that we can get rid of the null energy condition in exchange for replacing the classical by the quantum expansion in the theorem. So the derivative of the quantum expansion is not increasing in all quantum states. All right, so just to repeat, to connect this with what I said earlier in my alternative history of how Hawking discovered the second law of thermodynamics, the idea is the same here. We started with a GR theorem. We lifted it up to some kind of semi-classical quantum gravity statement. Now the next step is to get rid of the gravity part and learn something about quantum field theory. Before I do that, I should say that there are many other interesting things that I could say about the quantum focusing conjecture. It's an incredibly powerful conjecture. I probably won't have time. I might have time at the end of the talk. But it implies a host of other things, some of which are new, and some of which are old but interesting. So it's really, for example, it implies various entropy bounds, but makes them more precise. But now let's talk about how to get down to quantum field theory and get rid of G Newton. Okay? And then we get something called the quantum null energy condition, which we can actually prove. All right. So looking at the definition of the quantum expansion, we see that this has the structure of a classical part, which dominates, and a quantum part, which is the first correction in an expansion in GH bar. Okay. So for example, if I choose an initial surface in Minkowski space, this classical part doesn't have an H bar in it. It's just some geometric quantity which is going to be much larger in the limit as H bar becomes small than any of these correction terms. That's not the regime I want to be in. Okay. What I want to do, on the other hand, I also don't want to get rid of the classical part completely, and we don't really have to worry about that. What we can do instead, let me just go back for a moment. What we can do instead is consider situations where these two terms are actually of the same order, because the classical part starts out at 0, and then through gravity, through quantum field theory coupled to gravity, starts picking up a contribution which is then of order GH bar, so that these terms are both of the same magnitude. And it's really G that I'm interested in here. Okay. So there's recently been quite a lot of discussion about what exactly are the settings in which I can consider this type of special case derivation of a consequence of the quantum focusing conjecture. But here I'll focus on the simplest case, which is already, I think, quite interesting and covers a large class of settings that we care about, namely quantum field theory in Minkowski space. And I'm going to consider one of these null planes, so something like Z equals T in Minkowski space. Okay. So that is the kind of null surface that has vanishing expansion. Little theta, the classical theta, is just 0. Okay. But now let me couple this to gravity and assume that gravity is weak enough that I can treat this perturbatively, which is typically going to be true at least for a while. If I couple this to gravity, then gravity will induce some amount of focusing, which I can compute as a correction from Ray-Choudhury's equation, and which is going to depend on G Newton. Okay. So I'll go through this more slowly with equations in a moment, but just for the strategy. So in the end, what we're going to have is a term here that depends on G Newton, a term there that depends on G Newton, and then there might be additional terms in some expansion in G Newton. But at that point, we can take the G Newton goes to 0 limit. And since these two terms have a G Newton in it, and these ones have higher powers, what I'm going to get is only these two terms. And then I can cancel out the G Newton in the remainder and get a statement just about quantum field theory. Okay, so here's the formula version of this. So this is the quantum focusing conjecture. 0 is greater than or equal to the derivative of the quantum expansion. We can expand this out in terms of the classical expansion derivative plus some combination of second and first derivatives of the exterior entropy. Right. Then we use Ray-Choudhury's equation for the classical expansion derivative, which gives you terms that we've arranged to be 0 by our choice of surface. Shear squared and initial expansion are 0. And then the term that's proportional to G Newton that tells you that gravity is going to build up small bending of light rays on this surface. And it has the stress tensor expectation value in there. Right. And then out of these sort of information theory terms on the right, what survives is only the second derivative of the exterior entropy, because again, this gets multiplied by an expansion that's 0. Okay. So collecting the surviving terms, the ones that matter given the particular surface I applied the quantum focusing conjecture to, is this statement here, which we call the quantum null energy condition. On the left-hand side, looks like it's going to be a null energy condition, but it's the expectation value of the null components of the stress tensor. And then on the right-hand side, we have an information theoretic quantity, the second derivative of the exterior entropy under the deformation that we're taking. So this is actually something that was surprising to us at first, because there's, it's known that there's no local bound on the local expectation value of the stress tensor. But of course, we circumvent that here by having the actual upper bound be a non-local quantity, which is information theoretic. Okay. So one way of, that's one way of saying it. One way of thinking at it is a lower bound on the stress tensor. Another way of thinking about it is as an upper bound on how rapidly I can increase the rate at which I'm receiving information. Right? This is a second derivative of the exterior entropy. I can consider a setting where that translates into that kind of statement. So if I have a signal that I'm receiving from somebody far away, and that signal is going through a patch where it has negative energy, that's going to slow down the rate at which I'm receiving information. If it's positive, that means that at least in principle it would be possible for the rate to increase. So what I want to move on to now is the fact that since this is a quantum field theory statement, and I really made more of it than I should have, it follows very rapidly from GR once I include this quantum correction. It's incredibly easy to get it, right? But it should also be possible to derive it in quantum field theory. It's just that we hadn't thought of trying to do that because we didn't know the statement. Right? But there's no G Newton in here anymore. And we think we sort of understand quantum field theory. So we try to do that, and you get 20 pages like this just doing it for free bosonic fields. But it is possible. Okay. Roughly speaking, and I can only sketch the basic strategy of the proof, what happens is that when you have a null plane like that, it's generated by a bunch of null geodesics, which I can thicken a little bit with a cutoff into sort of pencils that generate the surface. Later you can take the limit where the pencils get infinitely thin. It's been realized, maybe by some people long ago, though certainly not by me, that the operator algebra factorizes over these pencils. This is something I learned from Aaron Wall. And it's something he demonstrated very nicely in a paper of his in 2011. This is, of course, not something that happens on a space-like slice, for example. If you rule that with some geodesics, even if you could do that, you wouldn't have, the operator algebra wouldn't have that kind of structure. What I mean by this literally is that the vacuum factorizes. I can write the vacuum as a product over the vacuum in each individual pencil. And so each pencil, since we are talking about the light-like limit here, is like a 1 + 1 dimensional conformal field theory. Moreover, since we are in more than 2 dimensions, and we're considering global states of finite energy, in the limit where the pencils are thin, the chance of having a particle on that pencil goes to 0. Right? And so that gives me an expansion parameter. The individual pencils are always very close to the vacuum. It's only when you look over many of them at the same time that you see that you're in an excited state. And so then the strategy is to take the state, well, what you really care about is the state on the pencil plus whatever is outside of the cut that you defined beyond the pencil on the other generators, and expand it into some, this is not the vacuum, into some state rho naught, in which the pencil is in the vacuum. So it's a product state of pencil vacuum plus whatever the rest is in. Plus some small correction to that, because the pencil isn't exactly in the vacuum. I think I'm calling multiple things sigma in this talk, and I apologize for that. But here sigma is a density operator, or a correction to a density operator. And you can then expand the von Neumann entropy into powers of sigma, which I'm labeling I = 0, 1, 2, and so on. If you do that, then after some semi-tedious work, you find that the 0th term is actually 0, plus the first term, their second derivative, would precisely saturate the quantum null energy condition. It's basically equal to the stress tensor with those coefficients in front of it that the quantum null energy condition has. So everything comes down to showing that the second, the S2 term, that its second derivative is negative. And that's pretty tedious, but you can show it using the replica trick applied to Renyi entropies. So that's what my students, Zach Fisher and Jason Kohler, and our postdoc, Stefan Leichenauer and Aaron Wall did. All right, so that was for free theories, and it was pretty hard to prove it. And we thought this was remarkable. I mean, that we can get a statement, pretty simple statement so easily from GR via this detour of semi-classical gravity. But we have to work so hard to prove it. We weren't particularly optimistic that we could do it for interacting theories, though Jason and Stefan were able to show, again, it's a rather elaborate paper, that you can show it for interacting theories with a gravity dual. So in those cases where you can compute the entropy using Ryuta-Yanagi and ADS-CFT duality, then you can prove the quantum null energy condition for such theories. It follows from a pretty fundamental property of subregion duality that if you narrow the region on the boundary that you get to look at, it has to tell you about less of the bulk than before. That's called entanglement wedge nesting. And so ultimately it comes down to that property of ADS-CFT. Okay, whoops, this didn't, okay, this is not optimal. Let me quickly exit here. I apparently did not recompile this after I last edited. Okay, now let's go back to preview. There we go. Sorry about that. So recently there have been quite a few papers initiated largely by Don and my own student, Jason, and I think this is Don's student, Fu. They explored the extension to higher curvature gravity and seemed to find a counterexample. But as Stefan then pointed out, the counterexample is, in fact, sort of violates effective field theory. You can't consider deformations that are supported on a cross-section that's smaller than the cutoff. So this particular example arose in Gauss-Bonnet theory, and when you smear over a large enough region, it just precisely gets resolved with no room to spare. So it actually works out very nicely. Another nice extension that Don and Jason and Fu began to explore is what happens when you try to extend the quantum null energy condition, optimistically to more general settings. I mean, we were in some sense very conservative and considered only null planes in Minkowski space or stationary surfaces more generally, but still there's much more general settings where you could hope that all the quantities in the equation are well defined and that the equation is actually correct, or the inequality. I think this was very thoroughly resolved by my students Chris Akers, Ven Chandrasekaran, Adam Levine, and Arvin, whose last name I still have trouble pronouncing, but I'm working on it, and also Stefan under his leadership. They showed that the same exact geometric conditions are necessary and sufficient for 3 different questions you could ask. Does the quantum focusing conjecture imply the quantum null energy condition? I'm not listing those conditions, they're not that interesting, but does ADS-CFT using Ryuta-Yanagi imply the quantum null energy condition? And thirdly, is the quantum null energy condition even well defined in the sense that the quantities are defined in a scheme-independent way? Very recently, just a few days ago, Tom Faulkner proved us all wrong and showed that it is in fact possible to prove the quantum null energy condition for interacting theories. And this paper is just mind-blowing. I can't say that I've completely worked through all of the details. It's very long. It's incredibly impressive, and I think we're going to learn a lot from this paper, and there'll be interesting extensions. But it's just as an extremely minimal summary, it basically combines techniques that were used in 2 recent proofs of the average null energy condition. One was sort of quantum information theoretic. The other was dependent on causality, and it was kind of weird that you had 2 different ways of proving the same result. Well, now we sort of know why. This is a weaker result, but you really need both things together, both techniques together, to prove the quantum null energy condition, which implies this is a special case. So I think I'm out of time. I want to make one more remark. I already said the quantum focusing theory conjecture also implies interesting other things, like the covariant entropy bound. I do want to close, just because this is Stephen's birthday party, I want to close with a new area theorem that Netta Engelhardt, who's here, and I stated and proved together. It can be proven from the null energy condition. It applies to things called holographic screens, which are basically if you have a sequence of null slices and you look at the largest area surface on each null slice, the statement is that that always has to increase. Again, it's violated for the usual reasons. Well, here's Netta. When the null energy condition is violated, but it can be fixed up by adding generalized entropy, by replacing the area with the generalized entropy. And then you get, in a sense, a second law for cosmology. You no longer need to have event horizons to make this statement. It's a much larger class of hypersurfaces to which that statement can now be made. It's in a sense a different statement, but the entropy outside a sequence of quantum holographic screens plus the area of those surfaces cannot decrease. That's a conjecture, but if you like the quantum focusing conjecture, it's really just a special case of that. It can be proven from that. So I think there's a very nice network of conjectures and to some extent proven theorems that we're exploring. So I'd like to close by wishing Stephen, who's not here, a happy birthday.
Okay, thank you very much. Any questions? Yes.
Thank you. Could you go back to one of the slides that shows the quantum null energy condition? Yeah. So from what came directly before, I missed the step of how and with what assumptions you identified the right-hand side with the average of the energy momentum tensor, and just wanted, so...
Identified the right-hand side with?
The left-hand side, sorry.
Oh.
So you have the right-hand side. Before you had the, focusing condition, quantum focusing condition, and then at some point you identify the left-hand side with the average of the energy momentum tensor. Just
repeat that.
Oh,
yeah.
Oh, it's sorry.
So here's a sort of a dividing line here,
right?
In the second line,
right?
Everything to the left of the stick comes from little theta prime.
Yeah.
So that's the classical stuff, and in the setting we're considering, the only term that it contributes is the stress tensor.
Okay. Right.
And then this is the quantum stuff that comes from the. Yeah.
Great. Thank you.
Yeah, so you mentioned that Don Maroff and colleagues had looked at this in curve space and had some counterexamples, but you had this long list of authors that said if you impose a certain set of conditions, then all of these things are equivalent.
That was actually just one author. Let me go back to that. There were two papers by Don,
right?
Both of which were followed up by papers from my group.
Yes.
And I hope I can find them in a moment. Here we go. Yeah, so one was the extension to higher curvature gravity. That's where Don and friends claimed a counterexample.
Okay, I guess I meant the other.
And the other one is the extension to curvature. So that's really, you can now ask, well, more generally, can we find conditions that are broader than just saying null planes in Minkowski space, where this statement can be argued to hold and is well defined?
I see. So I guess I was just wondering, the conditions are on the surface that you're using, on the null surface, not on the underlying space-time. Is that correct?
The conditions are, well, they involve things like the extrinsic curvature.
Okay.
So in some sense, they involve both. But they're local to the place where you're deforming.
I was just wondering if they were sort of physically, if space-times that didn't satisfy this were somehow physically, if we would recognize them as physically unreasonable or...
No, not at all.
Yeah.
Not at all. It's just that, well, what's not clear is that there are any examples where this doesn't hold that aren't trivial. So you can find lots of examples where, the classical term just dominates completely, but then you would also have some scheme dependence. So it's not only true that, so if you took it literally, it would look like the condition becomes trivial. But mathematically speaking, it doesn't even quite make sense. But that's not because the space-time is bad.
Okay, thank you.
Okay.
Hi. I would like to know if in one of your assumptions, did you require for the entropy to be additive, or if that's free?
No.
Okay, cool.
Thank you. It's a good question. I mean, this is always a von Neumann entropy of the quantum fields restricted to one side of the surface. And so, in general, it will not satisfy any additivity properties.
Okay, one last question. Andy?
Could you go back to that slide you showed in response to the first question?
Yeah, hopefully.
Yeah.
That one?
No, the one just before that.
That
So
one?
you said that the right-hand side is non-local, but
Yeah.
if you're taking the size of this pencil to 0, why isn't that a local quantity?
Because I don't know if we have any chalk. It'd be so great if we could just draw a picture real quick. Is there any chalk? Perfect. Yeah. So, Andy's over there. I'll do it over there. So here's my surface. And I'm about to deform it a little bit like so. Okay, and when I do that, I'm going to start including a little electron here on one side of the surface. Okay. Now, how that electron changes S out, or also the second derivative of S out, depends on what is happening elsewhere. So it can depend on, for example, if I have another electron here, which is in an EPR state together with this one, so it's in a pure state, then when I move
So
from...
it's just non-local along the null generator, not in the directions transverse to the...
Now this is, so here are the null generators. Sorry, I didn't draw a very clear picture. This was my cut,
Yeah.
and these are the null generators. So here's one of them, and this is the one that where I'm deforming, right? And let's say I start with this cut, and I'm going to deform to that cut, right? So, and I'm going to look at this side. Okay. So initially I had an electron that was contributing to S out. Well, actually it wasn't, because it was entangled with this guy, so it was contributing nothing at all. Now I've moved it. Now that no more their electron is contributing, because its friend now is in a mixed state. And the friend is very far away. And in fact, the story changes again if I just move my cut over here, where I'm not deforming it, but just leaving it like there throughout the whole process. Now it goes the other way. So things, and of course the electron didn't have to be near the cut. It could have been very far away. So it depends on the entanglement structure of things that are near where I'm deforming with things that are arbitrarily far away.
I see. Now, also you said at the end of the day that the T canceled, and you just had to compute the positivity of this S2 double prime. Is it?
Yeah.
Doesn't that make it sound like it's
Negativity, yeah.
or negativity? Doesn't that make it sound like it's not really a bound on the energy density, because that's canceling on the right-hand side? It's some other quantity that's like an entropy that.
Well, I need the, I mean, I suppose you could ask what happens when we subtract, maybe that's what you're asking. What happens when I subtract from here S0 and S1?
Yeah.
Right? Then I get 0 on the other side, so I get a statement just about S2.
Right.
That's clearly true, given the structure of our proof. I don't know if it's true in interacting theories, but it's true in free theories. I just don't know how interesting it is. Because while this was technically how we proved it, it's not like the individual terms on the right-hand side, S0, S1, and so on, had any particularly interesting interpretation in my mind.
I see.
But you're right. One could have written it that way. It's just that this seems to be the way to write it, where it's most immediately clear they connect with things we might care about.
Right.
Okay, well, we should move on. So let's thank Raphael again.
Thank you.